Thank you very much, everyone. You just heard from Julian why it's important to put security testing into your continuous integration pipeline. What I want to talk about is how we can make that security testing smarter. And we make it smarter using the advances we've had in our field in the last 15 years. Advances that have made intelligence that was once required human beings now within the purview of our computers. Let me give you a simple example. Here's a small program, fits on one slide. This program has a bug in it. Who sees the bug? Show of hands. Oh, not so many people. So this program, if you feed it the input, BAD exclamation point, and only if you feed it that input, will crash. Now, if you wanted to find this bug, and I didn't give you the source code, you have a couple of options. Option one, try a bunch of different random inputs, see if it crashes. Well, we'll be waiting here for a long time. Another option that you might try, especially if you're in security, is you might start reverse engineering this binary. You might open up the debugger, single step through, and try to understand what the code is actually doing. And you would see in your mind that the first byte is being compared to B, the second byte is being compared to A, and so on. And you might then reason about what this code is doing. Today, we actually hire human beings to go through and do this kind of work. And what we do is we ask those human beings to go over very complicated pieces of code and parachute in, like firefighters, into places where they need to be found. So the key question today I want to talk about is how does that intelligence scale out? So as I mentioned, today we have these firefighters, and then they are human beings that we bring in on demand. How many people here have hired a security consultant for a security review? Okay, there's a couple people. Now, think about that. That required some time to set up, that required some lead time, and it required some understanding of the environment you want to drop them into. The other thing about security consultants that I find interesting is there's actually not that many people who are really good at the job. I was at security summer camp this past June, and there's only about 200, 300 people in the world who are really great, and a slightly larger but still small number who really know what they're doing. So that means our entire field is just one tragic accident away from having to restart from scratch. Now, what we've been able to do in the last 15 years, and you're going to hear more about it in the next talk, we have been able to create a new class of programs that automate some of the reasoning that you or I would use to find a bug like the one I showed you. So this is a sample of what that reasoning looks like. And this is live on the web. You can go to that URL and you can see a tutorial that will introduce you to this class of programs. There's this one called Z3. It happens to be from Microsoft, happens to be open source, but there's many others. And what this piece of code is doing is it's trying to ask the question, when is signed and unsigned comparison not the same? So if you've done any auditing of code, you might realize that one very common issue that comes up is that signed and unsigned integers have different rules for comparison. You can have a check, a signed comparison, that doesn't behave the way your developer expects. And that can lead to challenges if you're using that check to enforce some security property. So this is an example of a piece of code for one of these solvers that says, I want you to tell me when is a signed comparison not the same as an unsigned comparison. So all of that stuff with all the parentheses, what that's doing is it's just asking this solver, when are these two not the same? And you can actually go there in the web and you can ask the question and it will tell you, hey, this is the case, they're not the same at this point. So if you think back to the problem I showed you, the program on the very first slide, that is asking you to reason about different inputs to the program. Those questions can be transformed into language like this, and you'll hear more about that in the next talk. And those questions can be solved automatically using this new class of solvers. Now, the second big breakthrough that we're using is the ability to, at scale, take a complete record of the program as it executes. We call it time travel debugging. Now, to understand why this is important, here's a car crash. You might wonder Why did the car crash? You might look at the bumper being broken. You might look at the wheel being turned a certain way. But we all know that when a program crashes, there's just not that much that you can do to understand what was happening beforehand. Now imagine you had the ability to get a video of what the program was doing, kind of like this. Imagine you had the ability to understand frame by frame a video of the car before it crashed. We're now able to do that at scale for very large applications. Pretty much anything that runs on Windows, if the technology we have at Microsoft. And there's a number of other projects coming out for open source stuff. Now, what happens when we put that video together with the ability to automate reasoning? Well, this is what happens. Here's the problem again. Here's the code again. I can give it an initial input, the input good. It's not going to crash, but I can actually use that video I'm taking of the program, and I can automatically write down what is the program doing. I can see that the first byte is being compared to B, the second being compared to A, the third to B, and the last exclamation point. I can actually then feed that into an algorithm to say, how do I explore different parts of this program? I can say, in order to explore a new path, in order to increase coverage, I need to make that last if statement true. So there's a constraint that has to be true on the input. That last byte has to be equal to exclamation point. But how do I get there? Well, I get there by making the other if statements false. And those get fed into our solver. So we are now able to automatically extract from the program as it runs these constraints and feed them to a solver and come up with an entirely new test case that increases our coverage of the program. And we can repeat this process over and over and over again. What we do is we take a complete trace. We're able to create new test cases for every single if statement that we see in the program and systematically explore the state space of the program. Then what we do is we feed those back in. So we have a fully automatic process for creating new test cases. Now, what we like about this is twofold. First of all, as you heard from Julian, false positives are the bane of any automatic tool's existence. We're creating actual test cases, which we can then instrument the code for any kind of oracle for bad behavior. But second, we can use these test cases to create new symbolic executions, new runs of the program, in order to get closer and closer to, in this case, the BAD exclamation point that crashes. And so when I give this talk, sometimes I ask people, especially in security audiences, how long would it take you with a debugger to reverse engineer this code and find the crash? It would probably take me a whole afternoon. I'm actually not very good at this. I think the fastest I heard was at Microsoft Blue Hat. This really wonderful fellow who was just fresh off winning Pwn to Own said, I can do that in like 10 minutes. Well, with today's technology, you can do it in 2 on a laptop. That's what we have the ability to do now. If you can express your problem in terms of these solvers, and if you can write down the questions automatically, you can solve questions in a few minutes that used to take you hours or days. And to give you some data on that, this is a pointer to a paper we published that shows some data from how we use this on multiple versions of Windows and Office. We solved 3.4 billion constraints, and 90% of them we solved in a tenth of a second or less. Now, these solvers are not magic. They can't solve every single thing in the world, but they're getting really good at the kinds of problems that we care about in security. And I'll talk a little bit more at the end about what you can do to make them even better. So we had something at Microsoft that worked really well for us on premise. It's something that I had been working on, my colleagues had been working on, but it required a ton of work. Every single new version of Windows, there'd be a new way of testing it, would be a new bunch of integration. So what we realized is there needs to be a way to put this together into a service everyone can use. Now, what we do is we've created something where people can upload the binaries they want to test. And we went out, we talked to actual customers. How does this work? What's going to happen? What is the right way for this to work for you? Originally, I naively believed that people could give me a zip file full of all their binaries, and that would be it. It would be great. It turns out that people have dependencies. They have kernel drivers. They have registry keys. They have other things they need to install before anything works. But the core point is we define something where you can submit some binaries, just the same way you heard Julian talking about submitting binaries in continuous integration pipeline. And then we run multiple techniques of testing. So the other thing we learned when we started thinking about the cloud, and we moved out of our on-premise mindset and into the cloud, is we realized, yes, it's great we have this incredible, fantastic constraint-solving technology. But it's also true that fully 2/3 of the bugs overall in Windows 7 were found by just random dumb fuzzing, just randomly throwing inputs at the problem. We now have the ability to create, using the cloud, multiple different machines that are all using different kinds of tests. And we've actually heard from people who've hired security consultants that one of the things that they get out of that engagement is new testing techniques, new fuzzers, new custom harnesses for their use cases. With the cloud, we can put that all together into one large lab that's spun up on demand. From that, we then take all of the test cases we have and we run them through a triage process that helps us understand what are the high-value test cases. You just heard from Julian that it's important to socialize the requirements and understand what is the bug bar. That can be implemented in code, which is then applied to all the actual test cases that you see in a particular environment for a particular customer. And then finally, of course, you take action. Now, maybe you fix the bugs. But how many people here depend on code that they don't control? Open source libraries, closed source vendor code. You know, how many people here have code that they just can't patch? Okay, pretty much everybody. And so what this really does is it helps you analyze the risk. It helps you understand what's high risk, what's low risk, and take action. For example, we've seen people build sandboxes around code that they can't patch. Other times, people have made the call to get rid of the code altogether. And finally, of course, if you have a relationship with the upstream, you can go ask them to patch it, but with a specific test case that causes a specific crash. And we've actually seen this happen at Microsoft using our technology to go and upstream reports to code that was being licensed in to let people know that they needed to fix something. So this all comes together. We've been very pleased to have some people come and use it in their professional lives. There's actually a video you can go look at. What they were able to do is they were able to quintuple the number of teams who are using fuzzing technology. And they're able to use this solver technology I showed you without having to know anything about how it works. Because the power of the cloud is we can wrap up all of our complicated solving inside of a cloud service and make it available to everyone. And I was particularly gratified when I found out that their product that they were testing with us was actually being used by Deschutes Brewery to move their operations and their data into the cloud. So we are fuzzing more so they can do more so that Deschutes can brew more. So that's part of our journey in one silo of the application security pipeline. We've helped people use this technology to find bugs they would miss otherwise at greater scale. But if I look ahead at what our opportunity is, our opportunity is to look across multiple silos. Now let me explain what I mean by that. We have another project, it's not mine, but I want to let you know about it, called SetGuru. SetGuru is a project that works in the Azure networking stack. And if you go there, you can get a link to the technical report that gives you all the details about it. How many people here have misconfigured a router or a firewall? You know, okay, a lot of people, right? Now, if I were to tell you that roughly 3/4 of outages come from people accidentally misconfiguring firewalls, would you believe me? Yeah, because we've all been there. What SetGuru does is it uses the same solver I showed you earlier, but what it does is different. What it does is it implements regression testing, smart regression testing, for changes to firewall rules. So the Azure team has defined a set of invariants that need to hold across the entire estate of the Azure routers and firewalls. And every time I make a change or you make a change or someone else makes a change, that change gets sucked up, sent into the solver, converted into logical formulas, and we ask questions like, is this going to violate the invariant that we want? What is the set of overall changes that we're going to make if we make this? And this is crucial because, of course, these are all being changed as needed by a number of people who don't necessarily need to talk to each other. And because we can put all of that smarts into a centralized service that can reason about these things, we can achieve 0.3 of a second per check, so a very low overhead. We can create a smart regression testing where when you make changes, we can easily see if the new firewall rule is equivalent to the old one. And they use this actually to cut in 1/3 the number of rules that they had. So their old system had been built up over years and years and years. It's a rat's nest. No one wants to touch it. No one knows it can be touched. Using this kind of technology, you can say, let me reduce something. Let me make sure that it still implements the invariants that I want and make it smaller and smaller and smaller. So that's a second silo. That's the network silo where we can use this reasoning technology. And we can use it at scale because you can see again in the paper that it's being used in production today. So where are we going with this? You've heard from Julian that it's important to do automatic testing. I've just told you in 2 different silos how we can use today's reasoning technologies to make that testing smarter. And you're going to hear from Neston in just a minute about how you can actually make this work for your problem. But what is happening ahead? Well, I think what's ahead is sharing this analysis between silos. Why shouldn't your network know about the testing that was done on your application? Why shouldn't your application know about your network architecture? Why shouldn't your DevOps people know about the code quality of all the pieces of code, open source, closed source, whatever it is, that are going into your environment? If I look at the world today, I look at the need for control and the move towards smaller combined engineering teams, the more I am convinced that this kind of reasoning at scale across silos is the only way that we can make sense of the complexity and the speed that our businesses desire. For example, we now have a huge movement towards security credit scores that we see in the marketplace that depend today on all kinds of inputs. Why shouldn't they depend on the analysis that a code has been through as it's been running? Why shouldn't they depend on all of the different configuration changes that you've made when you're deploying it? Now, this is not real today, but if I look ahead at where we can go, this kind of sharing analysis across silos and scaling the analysis of the power of the cloud and treating our infrastructure as code and taking that seriously, meaning we can reason about that code at scale, opens the door to a new set of opportunities. So what can you do next? Well, first of all, the Z3 solver I talked about is open source. You can learn to use it. You can download the code. You can play with it. You can give pull requests. It's not the only solver, but it happens to be the one I'm familiar with and works very well for me. Second, there's actually a competition for solving benchmarks. If you have a problem that you think might benefit from this, stay for the next talk. Hear Neston on how you can actually formalize it, and then contribute your benchmark to the SMT competition, where then everyone who works in these solvers will fight with each other to make their solver fast for your problem. Watch the next talk, and then think about how to build the future. I just want to leave you with one quote that I think is particularly exciting when I think about this whole area. It goes back to David Hilbert, who was one of the founders of formalism in mathematics, and in a way, the sort of great-great-grandfather of all of us here in this room. Now, he had this dream that we could have a decision procedure for reasoning about all of mathematics. Now, that was not to come true, but the thing that is inscribed on his gravestone is, we must know and we will know, and I think we can do that for security. Thank you.